Yeah, as David said, I'm Sophie Darcy. I'm a PhD student at the Colorado School of Mines, and today I'll be talking about some of my work, which uses numerical modeling at the hill slope scale to look at how headwater stream catchments will change in the face of a changing climate. And I just started on these models, so I don't have a ton of results, but today I'll kind of talk about the motivation and just some field work that some colleagues have done that are inspiring the models, and just like the preliminary start. I have some timer here. Let me turn that off. Oh no. Sorry, I'm struggling. Okay. And then, cool. Okay, so headwater streams are the smallest, most upstream portions of our river networks. And although they're small, they make up around 70%, first and second order streams make up around 70% of total stream length, and they contribute water and solutes to our downstream rivers and lakes. And so here you see on the left, Hotel Gulch, which is a headwater stream that I'll be talking about today in the mountains of Colorado. And although it's really small and cute, it ends up feeding into Trout Creek, which eventually makes its way to the Platte River, which eventually flows into the mighty Mississippi, which drains into the Gulf of Mexico. So although these streams are really small, they end up supporting these much larger bodies of water that are really important for water resources and societies. And as Dr. Sawyer talked about the other day, these lower order streams play an important role in these different chemical cycles. So here she was giving some model results showing how lower order streams remove nitrate more effectively. So I'm not going to be talking about nitrate today, but I just thought this was another important role that these streams play in our environment. And so here's a conceptual model of the type of system I'll be talking about today. On the top layer we have, can I point? No, this one? On the top layer we have this high permeability soil or sediment, and beneath that we have a saprolite or weathered bedrock that has fractures in it, and below that we have a fractured bedrock. In the case of the sites I study, it's usually low permeability crystalline rock like granite, gneiss, or schist, and so the main flow pathways through the deep subsurface are through the fracture network. And these types of headwater streams are often supported by snowpack and groundwater, and so here we have snowpack that melts and runs off into the stream, but it also melts and infiltrates into the subsurface, becoming groundwater, which eventually makes its way to the stream. Okay. But unfortunately, it is what it is, snowpack is predicted to decrease for the western United States. So on the left, here we have the percent area of this upper Colorado River basin, which is not too far from the area I study. But here we see the percent area of snowpack of that basin that is low to no snow, increasing by the end of the 21st century. And then here on the right, for the Rockies Mountains, which are also in Colorado near the area I study, we see a predicted decrease in snow water equivalent, so a decrease in snowpack by the end of the 21st century for this region. And so what this means is if the area of snowpack and the depth of the snowpack is predicted to decrease, this might mean less area and less snow to melt and infiltrate into the subsurface and recharge groundwater. So we might see decrease in groundwater recharge. And then also this could have effects on, the chemistry, right? If there's less water recharging and spending different amounts of time in the subsurface, we might see different solute flux to the stream. And then here we see plots showing, and I know Christian told us not to trust these kinds of maps today, but I think we'll just use it for this time. Here we see the fraction of snow-derived runoff over total runoff. In yellow, we have more snow-derived runoff, and in blue, we have more rain-derived runoff. And here is the area I study. It's mostly snow-derived runoff. And then here we see projections for a mid-level or middle-of-the-road climate scenario showing projections for change in the fraction of snow-derived runoff. And here we see the yellow indicates a 5 to 15% decrease, or maybe 5 to 10% decrease in the fraction of runoff that is derived from snow. So we're seeing more runoff from rain, less runoff from snow. This changes the timing of things, right? This changes the timing of stream flow possibly. This changes the amount of recharge available, maybe, so that's, given that, I'm wondering how headwater streams will respond to changes in climate. And the approach that I'm using is a kind of integrated field and modeling approach. So a lot of my colleagues have done really great field work in these types of headwater catchments in Colorado, collecting a lot of field data, developing knowledge and intuition about these systems. And then the part I'm working on now, and we'll kind of talk about today, is the creating models that are informed and constrained by this field data and at the hillslope scale right now. And then ideally run these models for predicted climate change scenarios, and identify like the key parameters controlling changes in headwater streams with the chemistry and the flow, and then as needed more field work and just like continue that cycle until I guess we have the answers we need, I don't know. So here's the field site. It's Hotel Gulch. This is like a 2-kilometer long headwater stream in the Manitou Experimental Forest, which is located here. It's a long-term monitoring site located south of Denver in Colorado, which is here in the US, on the east side of the Rocky Mountains. And yeah, this is the top of the catchment, site 8, and here's the bottom of the catchment. And so each of these sites was instrumented with a stilling well in the stream and then a shallow groundwater piezometer not far from the stream to take measurements. And then the depth of the regolith, or the sediment beneath or at the bottom of the streams and around these sites varies. Like sites 1 through 6 at the bottom of the catchment, we see more like 1.5 to 2 meters depth of sediment. And then at the top, we have much deeper sediments. And beneath all of it is a fractured Pikes Peak granite bedrock, and we know from a previous study that the stream is mostly being sourced by adjacent hill slopes contributing groundwater. And so we also have this variation in the catchment of topographic gradient. So at the top, this is fun. Okay, at the top we have like a floodplain area, so we have more shallow slopes and deeper alluvial sediments, while at the middle of the catchment we see we have our steepest slopes and we have less alluvial sediments. And so here again on the left, here's a picture of one of the sites at Hotel Gulch. You can see the small stilling well and this shallow groundwater piezometer. And so when I talk about like groundwater measurements being taken here, they're close to the stream. They're not like super, they're close to the stream and they're kind of at the depth of the bedrock. And this is Sarah Works, who did all this field work, standing on some granite looking at the watershed. And so I'm glad Camille talked about groundwater age, but really what it is if I were to take a sample of groundwater, it's basically the average time that each of those water molecules spent in the subsurface before I took that sample. And I think it's a really interesting idea. Well, one, I think it's cool to think about that water is old or young, but also it can tell us about the storage and transport of water in a system. Maybe it can knowing the distribution of ages, maybe it can tell us about recharge rates, like if there's a consistent and wide distribution of ages, then maybe, that tells us that recharge is consistent in a system. And maybe it can also help us with contaminant transport, right? Like if we know how old water can be in a catchment, then we know maybe how long things can stick around and what remediation strategies might be useful. And so groundwater samples were taken at each of these sites in June and September for 1 year, or for 2021, I guess it doesn't matter. So groundwater samples were taken, and then CFC and tritium age dating methods were used to estimate mean groundwater age for these samples. And those are good methods for, estimating mean groundwater age for relatively young water, so like 70 years-ish. And these are the results. So on the y-axis, we have estimated mean age in years, and on the x-axis, we have site ID. And these colors are just, each site has a unique color. And then the circles indicate the groundwater ages for the samples in June, and the squares are for September. And as you can see, there's an increase in groundwater age seasonally at most of these sites. And this is because in June, there's a large flux of snowmelt to the stream, bringing relatively young water and lowering the age. Whereas in September, we're mostly, a lower flow and more groundwater supported flow. So we're seeing relatively older mean ages. And I think something else interesting is I would kind of expect that the oldest water would be at the bottom of the catchment because everything's feeding into it, but actually we're seeing the oldest water at the very top of the catchment at site 8. And again, we don't have to take these as exact, they're estimates of mean age, but I think it's interesting to look at the, relative ages between the sites. And so what's possibly controlling, these differences in age across sites? So here are two correlations that I think are really interesting. Here's a correlation between June estimated mean age and slopes. So here we're seeing at shallower slopes we have older water, shallower slopes we have older water, and steeper slopes we have younger water. And then here this is age against stream bed hydraulic conductivity. And so we're seeing for less hydraulically conductive stream bed, older water, and more conductive, we're seeing younger water. And so here's a conceptual diagram that's kind of summing up the ideas that come from these correlations. And the idea is, like water in the steeper slopes is maybe flowing faster, it's less time to infiltrate into the deeper subsurface. We also have a more conductive stream bed, so water that is reaching the stream in the steep slopes is relatively younger compared to the shallow slopes where water is flowing more slowly, has more time to infiltrate into the subsurface. And then we also have this low conductivity alluvial silt that is providing this buffer area for mixing and storage, and that may lead to older groundwater in these flatter areas. And so Works et al. Put out some predictions for the future climate, and they predicted in steeper slopes that we might see periods of stream drying more often, and in the shallow slopes that we will see maybe lower but persistent surface flow. And in both scenarios for steep or shallow slopes, they're predicting a drop of the water table and a mean, an increase in mean groundwater age. And so to me this makes sense, but I want to use numerical modeling as a tool to kind of explore these hypotheses further. And so I'm using modeling because field samples of age and just field samples in general are limited, as we know. And then at best, field samples can only give us an estimate of mean age, whereas modeling can give us a distribution, right? We can output whatever we want. We could get mins, maxes. We can look at different things that we can't just with field data. And then obviously modeling allows us to look possibly into the future at different scenarios. And I have reactive in parentheses because right now I only have passive tracer species in my model, but going forward I will be looking at dissolution of primary minerals and precipitation of clays, so it will be reactive in the future, but yeah. So here I created model domains for 8 sites at Hotel Gulch. And right now the only difference between these is their slope angle. In reality, the regolith depths are different, the sediment depths are different, and the stream bed hydraulic conductivity is different, but I have to add that. We created these by generating 3-dimensional discrete fracture networks using DFN works, and then creating a fracture that's the shape of the hill slope and intersecting it with the 3-dimensional fracture network to get a 2D domain. And here you see blue shows our low permeability granite, and then our high permeability areas are the sediment at the top and the fractures. And here's a picture from the boat, which was a really fun experience. Thank you for organizing it. But here I took this picture because it reminded me, it's fractured granite, and these fractures look kind of orthogonal, and it kind of reminded me of these black and white pictures from this thesis in 1975 that looked at the fracture families in the Pikes Peak granite, which is the granite in the area I study. And so what this Blair identified were 3 different orthogonal fracture families. And so that's kind of what I put in to identify specify the orientations of my discrete fracture network. Okay, so here's just, again, use DFN works to create the fracture network, and Legrit and DFN works to create the mesh. And then I use pFlowTran to simulate flow and transport of passive tracers. And so here's our domain, and the model is basically just infiltrating, at this point, it's just infiltrating water consistently throughout time, 77 years, through the top face here. And then for each year, we have a different tracer that kind of tags it, so we know how old it is. So in 1950, we have tracer 1950, 1951, we have tracer 1951, which is just really a brute force way of trying to track the water, but I thought I'd give it a go. And here, so I'm going to show a video of just an example of one of the tracers in yellow infiltrating through the subsurface and going through the fractures and coming out at our outlet at the red star, or not, right? And so yeah, you can see the tracer coming into the surface, quickly draining out of that top sediment layer, some of it being diverted through the fracture network, and then a lot of it just like draining out through to the outlet, except some of it stuck around in the edges in our boundaries. And so what we can do is our model can output concentrations and water mass and things like that at this star here at the outlet, and we can kind of calculate the proportion of water from each year over the total amount of water, or the total amount of tracers there. And so this is a crazy slide, but basically here on the y-axis that we have that proportion of water from each year over the total amount of water. And so each color is each color of the rainbow is a different year. And blue is 1950 and red is 2021. And okay, why did I put this on here? I put this on here because it's okay, so it looks pretty uniform, right? We had constant recharge through the model, so it's not going to give us realistic results. But I think it does tell us that, I don't know, I think I can use this in the future to plot, just look at how water is moving throughout time at the different sites. And then I guess the other thing here is that this decline right here just shows me I didn't run my model for long enough before I added the tracers, and I didn't reach like a steady state. And so that's definitely something that needs to be improved. But then I was like, okay, even though it's like, obviously a poor representation of the site at this point, I wanted to try to estimate mean groundwater age. And so I'm calculating mean groundwater age as a weighted mean. And so at that outlet, at a certain point in time, I'm calculating the weights as that the amount of moles of a certain tracer from each year over the total moles coming out, and then getting a mean groundwater age of 2.7 years. Which I don't know if I forgot to point out the ages on that original graph, but they were more like 10 to 55 years. And so there's obviously a lot of differences between the model and reality, but I think the primary one responsible for this is the fact that the recharge I put in was just a constant rate all the time, but actually recharge is very transient. And so I think actually the transient nature of infiltration is what's controlling, water sticking around in this system based on just this first crazy model run. So obviously, there's a lot to do. I need to run my model longer to reach steady state before I add tracers. I think next I'll introduce like a variable, like maybe a periodic signal with different amplitudes, or maybe increasing or decreasing of infiltration to see how the model responds. And then ideally I want to get, use data and maybe more local scale models of like recharge or infiltration to recreate past conditions, and hopefully get something where we can compare our model to the field data we have, and then run it into the future for different climate scenarios, and hopefully learn something and move it forward. So my conclusions, groundwater age vary across site at Manitou, and are correlated. The ages are mean groundwater age is correlated with topographic gradient and streambed hydraulic conductivity. And we've developed a 2D hill slope model with a discrete fracture network to look at, to hopefully get at mean groundwater. We can hopefully get at mean groundwater age from our model. And I guess I just put this in here. I think the hill slope scale is a great scale to learn more about these processes, but I guess it depends on what you're looking at. These are references, and that's that. Thank you for your attention.
Thank you, Sophie, having the courage to present work in progress. Challenging thing to do sometimes. Do you have questions?
Yeah. Thank you for the presentation. But when you take the mean travel time, the distribution can be very wide, depending on the structure of the system and so on and so on. But the mean is very simple. It's the volume where the flow takes place divided by the flow.
Where's the what? Sorry, I couldn't hear.
The volume where the flow takes place, the porosity, if you want, divided by the flow.
Oh, like the transit time.
The discharge. And you can have transient effect. But in stationary mode, this is like that. So it means that the stationary mode, for instance, you don't care about permeability. Except if you modify the volume. See, and if the the recharge is constant, the total flow is constant. And so the mean is very simple, if you accept non-stationary effect, except some measurement effects also, because if you don't measure the total distribution and if you have a long tail of travel time, then you can have a sort of cutoff which can modify the mean. But in theory, the mean is simple. So if you have the same recharge, and if you have different travel time, different age at the end, it means that you have different volume where flow takes place. Okay?
Yeah.
So if you do that, I think you can analyze your data differently.
Oh, even if there's just like preliminary steady state situation. Okay. Thank you. Thank you. Sabrina. Oh, yeah, sorry.
I haven't seen DFN works used for a hill slope before. Can you tell me more about how you got like the DFNs that you ran your simulations through?
I guess this one. We generated a 3-dimensional discrete fracture network, and then we defined we have a boundary file that defines like the vertices of the shape, the hill slope shape, as defined by, like the slope that were measured in the field. And then we said, oh, this is a fracture, intersect this fracture with all the other fractures, and then just give it, give us the intersection, I guess.
How hard is it for water to come through that first diagonal fracture?
The first, like that one there?
The one that's defining your hill slope.
This one?
So you have this red line that like makes the perimeter of the triangle, right?
Oh, this one? Oh, that's not a fracture. That water drains through there really easily because it's a higher porosity and permeability because it's supposed to be the sediments. So if you look at this, it will go through, drain out of that really quickly, but then some of it diverts before it makes its way to the outlet.
Okay, I see how you did it. Thank you.
When you derive mean age from CFCs, you assume an age distribution. Which one have you chosen here?
So that's not actually my work, that's Sarah's work. I don't know, I did it like this. I could just use this. I put something at the back, maybe. This was from her paper. I think she did a combination of these different mixing lines. I'm not sure if this helps. I'm just learning about these methods, so yeah. Okay.
Any more questions?
Just kind of following up on Philippe, you put on 35 centimeters a day, and it took 2 point something odd years. What do you estimate the pore volume of your cracks were?
Oh, I haven't done that calculation, but I don't think the pore volume of the whole domain.
What's the porosity like that in that picture?
Yeah.
What's the total pore volume, do you think?
Of the whole domain?
Just of the crack.
Of just the fractures? I would have to, wait, let me look at something. I would have to think about that. We set the fracture permeability, fracture porosity to 0.9. So I guess it just depends on the area, I guess, of the fractures, which I would have to calculate. So I'm not sure in the moment.
Let's say it took 55 years.
Yeah.
How could a non-sorbing compound take 55 years through those fractures? What are the two variables that you could change compared to the 2.7 years?
You think, what could I change in the model?
Yeah, it could take that much longer, 20 times longer.
Yeah, well, I think it's the fact that the recharge is not a steady thing. I think we're maybe getting water. I don't know, the way I think about it is like if there's these moments where it's like there's water coming in, moments they're not, that things maybe can get stuck in these like different, I think it's more like the fracture network, like things could get stuck in the dead ends for longer and maybe take more time to get out, I guess, depending on these fluxes of water. I'm not really sure. That's hopefully something I'll see next.
Well, it could be maybe, it's either the rate of recharge, if it was 3.5 centimeters effectively, now go 10 times slower.
Yeah.
And then if there were diffusion into the main rock, you might not get it back for a whole long time. That would be real heavy tails.
Yeah.
it seems like, or the volume of cracks could be a lot bigger.
Yeah.
And that kind of piston flow model is a good way to kind of start maybe conceptualizing it.
Thank you.
Any more questions? All right, let's thank Sophie.